Today I would like to continue our observational overview of active galactic nuclei. And today we are going to start by talking about how we find active galactic nuclei throughout the universe. And once we've completed that, we will also talk briefly about terminology and how we refer to these active galactic nuclei. So it is clear that active galactic nuclei benefit greatly from multi-wavelength surveys. As we've talked about in the previous lecture, we know that active galactic nuclei are substantial emitters over 10 or more decades of frequency. And so we can utilize a broad range of surveys at many different wavelengths to find AGNs and to study them. And indeed, I would argue that for more than 80 years, most of what we know about active galactic nuclei has been driven, or at the least shaped, by our methods for finding them. We only find what we're able to find, and that ultimately then shapes the conclusions that we draw about active galactic nuclei. And I'll say more about that as we go through this presentation. I would say that this whole topic of multi-wavelength AGN surveys has been a huge success story. I've been involved in this endeavor for about 25 years now, and there have been some big successes that the community as a whole has made over those 25 years. We have made big advances, for example, in understanding the contribution of active galactic nuclei to the various cosmic background radiations. We understand now fairly clearly where AGNs contribute substantially, where they do not, and so on. We also have succeeded, we believe, in revealing most, or at least much, of obscured supermassive black hole growth out in the universe. We can find sources that are highly obscured that we previously were not able to identify as active galactic nuclei. Our multi-wavelength surveys have also totally changed our understanding of how the AGN population evolves. We now know that not all AGNs evolve like the luminous quasars do, but in fact AGN evolution is highly luminosity dependent. And along with that, we have also come to have a better understanding of what I refer to as the cosmic balance of power. That is, since the formation of the galaxies, what is the main source of power generation in the universe? Is it nuclear fusion in stars, or is it accretion onto supermassive black holes? We think we have a pretty good answer to that issue as well. And I'll talk about that in more detail later on. To give you the brief answer, we think stars, in fact, win and dominate the cosmic balance of power, and growing supermassive black holes have a significant but secondary contribution. Also, we now have a much better understanding of high redshift active galactic nuclei, how they came about, and we have a better understanding of how much of a contribution they make, for example, to the reionization of the universe. And then finally, we have also made a strong progress over the past 25 years in understanding the connections between active galactic nuclei and the galaxies in which they live, as well as connections between active galactic nuclei and cosmic large-scale structures. So all of those together, that's a pretty good record of success over 25 years. We've made a lot of advances, and it's sort of gratifying to see how far the community has come working on these matters. Okay, so then, when talking about these surveys, I do have a few brief introductory points. First of all, this is sort of similar to the apologies or warnings I gave in the last lecture as well. Multi-wavelength AGN surveys is an enormous field. There are many detailed review articles, I'll show you some of those at the end, as well as indeed entire conferences that have been held on multi-wavelength AGN surveys. In fact, here are little snippets showing three such conferences. Here's a conference that was held in Armenia, entirely focused on multi-wavelength AGN surveys and studies. Here is a conference that was held in Harbin, China, on X-ray surveys, primarily of active galactic nuclei. And then here is a conference on the VLA Sky Survey, which had a significant focus on active galactic nuclei. So there are many conferences that have focused on or substantially included multi-wavelength AGN selection. And then in addition, of course, there are thousands of papers in the literature. So as one would expect from the massive volume of work, I'm only going to be scratching the surface of this massive field. I will be aiming to give you some of the main ideas, while keeping the coverage not too dense and still accessible. And my apologies in advance if your personal favorite work is not covered here. Okay, so when one thinks about these surveys, these multi-wavelength surveys for active galactic nuclei, it is important that one utilize multiple multi-wavelength methods for finding them. We have many methods for finding active galactic nuclei, some as old as the subject itself. Carl Seifert, back in 1943, was doing spectroscopic selection of active galactic nuclei based on their strong emission lines. The studies that identified quasars by Martin Schmidt and colleagues were following up radio sources. And it has become clear that all the methods that we have devised for finding active galactic nuclei have limitations and selection effects. There's not a single method that's perfect. And it's crucial indeed to understand these limitations and selection effects. And that being said, we do now appreciate, I believe, and I think most people would agree, that some methods for finding active galactic nuclei are more complete and give purer samples than other ones. I think the X-ray methods, for example, are particularly good, although I may have my own biases in that regard. And so to get a complete census of the AGN population, one wants to apply as many methods as possible, hence the title of this slide, the value of multiple methods. One wants to apply as many methods as possible, which enables cross-checks, where if one method has a failure, another method may help to identify that failure and correct for it. And so we want to use multiple methods to get the most complete census of the AGN population out there in the universe. That being said, we do think that while none of these methods is perfect, we do have overall now a census of active galactic nuclei out in the universe that is sufficiently good to answer many key questions about, for example, the growth of supermassive black holes over cosmic time. And that is, again, significantly due to the advances made over the past 25 years. This is, again, a real advance of astronomy. Okay, a couple of other general points. One other general point I want to make is that these surveys for active galactic nuclei, and this is true of surveys more generally, almost always have a wedding cake type design. So what do I mean by that? Well, I mean that just as a wedding cake is layered in layers of increasing height or increasing depth is what we refer to for surveys, but then decreasing area, it's the same thing with surveys. We have some extremely sensitive surveys called deep surveys over relatively small areas of sky. We then have medium depth surveys over medium areas of sky. And then we have wide surveys, indeed some spanning the entire sky, but of lower sensitivity. And the deep, the medium, and the wide surveys are all needed for exploring the available discovery space for active galactic nuclei. They all have important roles to play, and they are best all used together to answer the questions that we have about active galactic nuclei. To show one example of this wedding cake type design, over here I show a plot that shows the flux limit versus the solid angle for X-ray surveys in this particular case. And so we have small area surveys with very great levels of sensitivity corresponding to the top of the wedding cake. We then have medium area surveys covering medium sensitivities corresponding to the sort of the medium layer of the wedding cake. And then we have wide area surveys, again, some covering the entire sky. We have X-ray surveys over the entire sky with lower sensitivity corresponding to the lowest layer of the wedding cake. So that's this general wedding cake design. I've shown it here with X-ray surveys in particular, but this is broadly applicable for all these surveys. And the basic reason for that, of course, is that, well, it becomes very expensive to conduct these extremely sensitive surveys. And the cost to conduct these extremely sensitive surveys over the entire sky, at least with present technology, is just too expensive. And so we can't do it. And so, generally, the progress of surveys for active galactic nuclei, or surveys in general, is pushing in this direction toward covering larger areas of sky with better sensitivity. Okay. And again, I'll show other examples of basically this same type of wedding cake type plot as I go through this talk to illustrate this basic wedding cake design that is omnipresent for all of these surveys. Another point is that, as I mentioned in the last lecture, we know that AGNs span an enormously wide range of luminosity, 9 or more orders of magnitude, as you can see just by looking at the x-axis of this plot, ranging from low luminosity active galactic nuclei to moderate luminosity active galactic nuclei, often referred to as Seyfert galaxies, up to the very powerful quasars. Okay. Now, unfortunately, no single survey method works perfectly and could plausibly be expected to work perfectly over this enormously broad range of luminosity. The techniques that we use to find quasars when we conduct these surveys are not very suitable when trying to identify moderate luminosity active galactic nuclei, or even less so, low luminosity active galactic nuclei. There are many reasons for that. One big one is that of host galaxies. Of course, these active galactic nuclei live in galaxies, and while for powerful quasars, like this one shown over here on the right, this is the prototypical quasar 3C273, while for powerful quasars, they almost completely outshine the galaxy in which they live, and thus the galaxy really doesn't cause many problems. That is not the case when one goes down to sort of moderate luminosity active galactic nuclei. This is the local Seyfert galaxy, NGC 4051, and you can see there's a substantial contribution of starlight here in the optical band, competing with the light from the active nucleus down here in the middle. And while for the case of NGC 4051, which is relatively nearby, we can go in with small aperture instruments and just study the nuclear region of this object, when one wants to study objects like NGC 4051, but at a much greater distance, when we want to study Seyfert-type active galaxies at a redshift of 0.5 or 1 or 2 or 3, well, these objects become very small on the sky, and we no longer have this luxury of being able to spatially separate out very well the AGN light from the starlight. And so one has to then devise approaches that address the level of host galaxy contamination in these systems. And this becomes even more important when one goes to low luminosity active galactic nuclei, where here the starlight from the galaxy may substantially overwhelm the light from the nucleus. And then, finding these objects can be very challenging even in the local universe, let alone at great distances. And so that's one big challenge that is a luminosity dependent one, where, again, the quasars outshine their host galaxies, often by large factors, whereas for the lower luminosity active galactic nuclei, that is not the case. Okay, then one final point on this introductory section is that, broadly speaking, and again, I'll give many more details about this as we go through the course, but broadly speaking, AGN appearances can be deceiving. There can, for example, be anisotropic obscuration or anisotropic emission that can make the appearance of an active galaxy deceiving in a way that I'll describe. So let's consider the case of anisotropic obscuration to begin with. We believe that many of these active galactic nuclei, in fact, we know that many of these active galactic nuclei out in the universe are obscured, often by large amounts of material, substantial column densities of material. And this material it probably has a variety of forms going from one active galactic nucleus to the next, but is often visualized as being in an equatorial configuration, perhaps a toroidal structure, as is shown here. So here is an equatorial obscuring torus, and the nuclear source down in here can be obscured when this source is viewed in an edge-on manner by this torus. Whereas in contrast, if you observe this same source in a polar direction, as I'm indicating here with the arrow, then the obscuration is much less, or there may be no obscuration, no material obscuration at least. And so the point here is that because this toroidal structure is anisotropic, if you observe the same object, the same beast, at different angles, if you observe it from an equatorial angle versus a polar angle, the phenomena you observe may be very different because, again, in the equatorial direction, the system may be heavily obscured. Much of the light from the nuclear source may not be able to get out directly because of this obscuring material, whereas in contrast, in a polar direction, it can get out. So that's one example of how AGN appearances can be deceiving. The same object can appear very different when viewed from different angles because of anisotropic obscuration. Not only do we believe there is obscuring material in this toroidal type structure, but moreover, we know that many active galactic nuclei launch outflows. Those outflows may often provide significant levels of obscuration. And furthermore, we know that many of these active galactic nuclei are thought to have accretion disks in them, and those accretion disks themselves may obscure some of the radiation being produced in the central regions. So there's a variety of potential anisotropic obscurers present in these active galactic nuclei. Okay, now let's go over to this right panel. Here I wish to also highlight the issue of anisotropic emission. We know that these active galactic nuclei can sometimes be anisotropic emitters. A classic example of that is the so-called blazars. These are systems that are thought to be launching, are known to be launching a powerful relativistic jet, and the blazars in particular are the systems where you have one of these powerful relativistic jets pointed almost exactly at Earth. And on account of that, you can get powerful relativistically beamed radiation boosted in the direction of Earth that can overwhelm a mission that you otherwise would be able to see because it's being outshined by this brilliant beamed emission. So that's another challenge, that of anisotropic emission. Not only can you have anisotropic emission associated with jets, but we also, for example, expect that accretion disks will have significant levels of emission anisotropy due to, for example, limb darkening, like that of the sun. Accretion disks viewed from different angles may are expected to have significantly different emission properties due to, again, intrinsic obscuration by the material of the disk itself. So AGN appearances can be deceiving, and here are a couple of examples of how that can be the case, and one needs to keep these things in mind when one is trying to conduct surveys for active galactic nuclei. Okay, so now I would like to move on and start talking about the current surveys that we have conducted for active galactic nuclei and their results. I'm going to break this down into ground-based surveys first, and I'll talk about those for a while, and then I will talk about space-based surveys, and I'll motivate with a couple of slides for each one of these sets why I think this is an appropriate way to break things down. So first of all, if you consider ground-based surveys, well, they can be conducted in the optical, near-infrared, mid-infrared, and radio windows. Here is the optical window through which we observe the stars with our naked eyes. Here is the near-infrared and the mid-infrared windows which often have significant troubles with atmospheric obscuration at certain wavelengths, but at some other wavelengths, the light can get down to the Earth. And then we have the radio window here, okay, where you have this broadband radio window where things could be where observations could be conducted effectively from the ground. Now, data in these atmospheric windows can be obtained relatively economically from the ground, because you don't have to build a spacecraft and launch it up above the atmosphere and keep that operating in the very difficult space environment. The ground environment is much more friendly, and moreover, observatories operating in these windows can benefit quickly from the relentless growth in information technology. As new sensors are developed, they can be rapidly deployed on the same telescopes in the optical window, in the near infrared and mid infrared, and in the radio window. Or similarly, as our ability to gather large amounts of data, store those data, move those data around improves, well, you can rapidly deploy the improved storage capabilities and data transfer capabilities on the ground. Whereas it's much harder to implement those things up in space, because space technology often lags far behind what we have available to us on the ground. And again, I'll clarify that more in a later slide. So as a result of these basic facts, most of the active galactic nuclei that we know of have been found in these bands, the optical bands, the near-infrared, mid-infrared bands, and the radio bands. And here, just to sort of show you these wedding cake plots. Here are wedding cake plots, in this case for optical imaging surveys. Now these are shown with magnitude, so high sensitivity surveys are up here, versus area. And again, you have sort of pencil beam, small area, extremely sensitive surveys, medium area, medium sensitivity surveys, and lower sensitivity, very wide area surveys over here. And here is the same basic thing, in this case for optical spectroscopic surveys, showing again limited magnitude versus area. And you have this same basic wedding cake design, which again is inevitable given the limited observing time that is available on these facilities. Okay. So let's talk about selection to begin with in the optical and near-infrared bands. So here, one typically selects active galactic nuclei via color selection. One is mainly looking at AGN light from the accretion disk, and I put that term in quotes because some people still debate whether the main source of light at these wavelengths is indeed an accretion disk. I think many people have good arguments that there is certainly elements of truth to that, but there are still challenges with the accretion disk model. But nevertheless, what we do see is optical emission, for example, that appears to be from a hot source in these active galactic nuclei, thought to be the accretion disk. And so what one can do is one can look for sources that are brighter in the ultraviolet than normal stars are, okay? And QSOs, or quasars, show an ultraviolet excess relative to stars with a comparable brightness in the visible. So you look for objects that have these big ultraviolet excesses, and many of them, not all, but many of them will be active galactic nuclei. In fact, powerful active galactic nuclei in general, the quasars. Now, these methods work best for unobscured quasars, because if you start adding dust reddening in these systems, well, that degrades this ultraviolet excess, making these systems harder to find, at least with that simple technique. Moreover, these approaches are best used for powerful active galactic nuclei, or quasars. As one goes to lower AGN luminosities, well, then that host galaxy light starts to come in, and that starts to dilute away the prominent ultraviolet excess signal that one would have when the AGN is fully dominant. Okay, so that's what one can do to select active galactic nuclei at relatively low redshifts, at redshifts up to about 2 to 2.5. This technique works pretty well. At higher redshifts, things get a little more complicated because absorption by the intergalactic medium comes in and starts absorbing quasars in the blue parts of their spectra. And that makes quasars very red in the blue part of the spectrum. And what one then can do is one can utilize multiple bands to select quasars lying at these high redshifts based upon their distinctive positions in color diagrams. Here are color diagrams showing G minus R versus U minus G color, R minus I versus G minus R, I minus Z versus R minus I. And the little points here are color coded, showing that quasars follow characteristic tracks in these color diagrams that depend upon their redshift. And that if you utilize multiple colors, as is being shown here, you can usually effectively separate quasars from stars, from the so-called stellar locus, and thereby avoid overwhelming contamination from large numbers of stars. And this method has worked quite well, and in fact it has been extended to even higher redshifts of 6 to 7.5 or so, by utilizing near-infrared data in conjunction with the optical data. And a prototypical example of optical-based selection of quasars in general is the Sloan Digital Sky Survey, or SDSS. It has used optical near-infrared color selection using multiple bands. In fact, these bands here, these data, I believe, are from the Sloan Digital Sky Survey, but it has used multiple bands to perform optical near-infrared color selection with great effectiveness over about a quarter or so of the sky. And in fact, that fraction is still going up because new observations from Sloan 5 are currently ongoing. And here is a relatively recent paper that shows the cumulative number of quasars found by the Sloan Digital Sky Survey over the 18 years that it has been operating. Okay? And over 18 years, the Sloan Digital Sky Survey has selected about 750,000 quasars. And this is usually done based on color selection, although they do utilize some other selection approaches as well. And all of these quasars here have been spectroscopically confirmed to be quasars, which is pretty impressive. This is an impressively large sample of quasars. And in fact, we have even more quasars now compared to what's shown in this plot from, for example, the Sloan Digital Sky Survey 5, which is currently using the Sloan telescope to find even more quasars spectroscopically, often in the southern sky now. And furthermore, other facilities like the DESI, the Dark Energy Spectroscopic Instrument, are obtaining spectra of many, many more quasars. I believe they're aiming to get something like 2.5 million quasar spectra once they are done with their survey. These quasars from Sloan span a wide range of redshift. You can see that here. They run from redshifts of, well, a small fraction, 0.2, 0.3, something like that, up to redshifts of above 4, and have been extended even up to redshifts of 5 and 6 with utilizing near-infrared bands as well. And inevitably, the quasars follow this strong correlation between luminosity and a redshift, such that as you go to higher redshift, you become less sensitive to the lower luminosity objects. And this is an inevitable correlation that is present at all flux-limited AGN surveys. Okay. So that's one technique for finding active galactic nuclei in the optical and near-infrared color selection. There are others as well, however. One can also utilize, for example, emission line selection. As we talked about in the last lecture, active galactic nuclei have strong, prominent, large equivalent width emission lines. And one can exploit strong emission lines to select active galactic nuclei. Here is one example. This is from the Hamburg Quasar Survey. And this shows a image of the sky, in this case in the B band, and then a corresponding image of that same area of sky, I believe, but this time taken with a transmission grating and a prism, and that spreads out the light from the observed sources, and one can look for strong emission lines in these low resolution spectra that have been gathered. And if one conducts these transmission grating and prism imaging surveys over large areas of sky, one can find large numbers of quasars that way. And that has been another effective way at finding quasars over the years. One can also perform blind spectroscopic surveys. As one example, the Hubble-Eberly telescope is presently conducting a large blind spectroscopic survey, which will find active galactic nuclei via, again, their strong emission lines. So that's another approach, emission line selection. Furthermore, one can also perform variability selection to find active galactic nuclei. We know active galactic nuclei are variable. I believe I showed this same plot in the first lecture. This is a 100-year B-band light curve of the prototypical quasar 3C273, and you see it's substantially variable. Okay, so what one can do is you can go out and find objects that are variable in multi-epoch optical data, for example. And ideally, you want to have a good number of epochs, and you want to identify objects that vary as you would expect AGN to vary, which is often quite distinctive from how, for example, many stellar systems vary. And so one can then weed out stars from active galactic nuclei just purely based on the variability data, and then you can follow up those sources to generate new interesting samples of active galactic nuclei. This has been done at bright flux levels, and it also has now been pushed to quite faint flux levels. Here are some nice results recently from DeChico et al., which investigate optical variability selection of active galactic nuclei in the very well-studied Cosmos field. Here they have 54 epochs of imaging data over a 3-year period. They can select large numbers of variable active galactic nuclei. These are these open triangles here, which stand out in having larger RMS deviations due to variability at a given magnitude than the general source population shown down there. And this has achieved pretty good completeness, about 59% completeness, I believe, compared to the X-ray AGNs in Cosmos. And it reaches to fairly faint flux levels. And you can generate fairly high sky densities of active galactic nuclei this way. Here they're reaching about 256 sources per square degree. And, if you did for example, an 18,000 square degree survey, such as planned by the Rubin Observatory, you could select about 4.6 million active galactic nuclei based on variability this way. So these variability approaches already are very valuable and will become even more valuable in the future as further wide field time domain surveys are conducted. And then finally, just to finish up with the optical and near-infrared survey, I want to highlight just a couple of examples of exceptional quasars that are found from optical near-infrared selection. You'll remember, for example, I pointed out earlier how reddening can cause trouble when trying to select quasars via this ultraviolet excess. However, when one has multiple bands, again, like things like G minus R, U minus G, R minus I minus Z, and so on, one can even select frequently reddened quasars, because while they don't have necessarily the strong ultraviolet excesses, their properties in this multidimensional color space still stand out from those of stars, for example, and allow them to be selected for targeting. And here, for example, are some nice examples of heavily reddened, luminous type 1 quasars at high redshift that have been enabled by optical and near-infrared imaging. And here again are nice examples of these systems, and they often have quite large luminosities, as you can see from these red data points here. Another example, going back to the spectroscopic selection, is here is the spectroscopic selection of type 2 quasars. So the Sloan Digital Sky Survey, as part of the BOSS component, took large numbers of spectra of interesting sources on the sky, and as a part of that, we're able to select interesting, strong emission line, so-called type 2 quasars. These are systems that are highly obscured due to that obscuring torus lying along the line of sight. But nevertheless, some of the emission lines are emitted from regions that are larger than that of the torus. And so one can select these objects because they still have these strong, prominent, large equivalent width, but relatively narrow emission lines. And here in this particular work, they have selected about 2,758 such objects. And here is a nice composite spectrum showing what these things look like. There are many other classes of exceptional active galactic nuclei as well that I will not be able to talk about, in order to keep this lecture fairly short. Okay, so that's optical and near-infrared selection. Now I want to finish our discussion of ground-based selection by talking also about radio surveys for active galactic nuclei. So at high radioluminosities, one is mainly looking at AGN light from the jets. And this emission can arise on a wide range of size scales. Sometimes this powerful radio emission is produced on rather small size scales, and sometimes it is produced on larger size scales and makes these beautiful extended jet structures that we observe from many radio-loud active galactic nuclei. Here are some nice examples here of extended jets observed in the radio. Now, radio surveys for active galactic nuclei have some real advantages. For example, we know that we have learned from many years of studying active galactic nuclei in these surveys that, in fact, almost all luminous radio sources turn out to be active galactic nuclei. So this is a rather pure method of selecting active galactic nuclei. Almost all the luminous radio sources are going to turn out to be active galactic nuclei of one type or another. That's a real advantage. Another advantage is modern radio surveys generally have high sensitivity, and they provide good positions, and they also provide useful morphological information, as I've already alluded to in this top panel. And here is your typical wedding cake plot, in this case, of area versus limiting sensitivity. Now the axes have been switched compared to the previous ones. But again, you have small area surveys. You have small area surveys with very high sensitivity. You have medium area surveys with medium sensitivity, and again, very wide area surveys with lower sensitivity. But over time, again, due to the improvements in technology, radio surveys, even over quite wide areas, have become very sensitive. And again, these surveys give you, high sensitivity. They give you good source position, so you can match the radio sources reliably to multi-wavelength counterparts and study them. And again, you get this nice morphological information as well. Now, those are the advantages of the radio surveys. Now, a important disadvantage of radio surveys is that they generally have high incompleteness. And that's because, as I alluded to, I believe in the previous lecture, only about 10% of active galactic nuclei have high radioluminosities. So while the sources with high radioluminosities will almost always turn out to be active galactic nuclei, you will not find all the active galactic nuclei this way, but only about 10% of them. Okay? And these are referred to, of course, as the radio-loud active galactic nuclei. In contrast, there are the radio-quiet active galactic nuclei. They do have some radio emission, but it is generally weak, almost by definition, given that they're radio quiet. And this makes searches challenging because while you may have active galactic nuclei present, radio quiet active galactic nuclei present at lower radioluminosities, you have many other radio sources as well that are not active galactic nuclei competing. For example, you often detect at fainter radioluminosities large numbers of star-forming galaxies, and you often have to sift through large numbers of these to find the rarer radio-quiet active galactic nuclei, and it becomes rather inefficient. Now, there's still a lot of interest, for example, in what is the nature of the radio emission from radio-quiet active galactic nuclei. I won't go into that in full detail here, but I will say that we think that many of these radio-quiet active galactic nuclei have radio emission that could come from small-scale jets, not the very powerful jets like for the radio loud systems, but they still have lower luminosity jets. Some have proposed that you may also have radio emission from the so-called accretion disk corona. That may produce radio emission. Outflowing winds from active galactic nuclei, if they have shocks in them, may also produce radio emission. And then you may have radio emission from star formation in the nuclear region as well. So again, there are many possible sources of radio emission from the radio-quiet AGNs, and clearly the situation is more complex than for the powerful radio-loud AGNs, where again, the emission is generally pretty clearly dominated by the relativistic jets. Okay. Now, another point I will make just in passing is that it is unfortunately still not really fundamentally understood why a minority of active galaxies are radio loud and learn a trick that allows them to launch these powerful relativistic jets, while the majority of active galactic nuclei, the remaining 90% down here, do not launch these powerful relativistic jets. What is the reason for that? Well, there are many possibilities that have been discussed. It may well be partly due to supermassive black hole spin. It may be due to the Eddington ratio. It may be due to magnetic flux and topology in the vicinity of the black hole. Some levels of magnetic flux or magnetic topologies may be more productive in launching jets than others. And furthermore, environment may play a role in whether an active galactic nucleus is able to launch powerful jets or not. So again, this is an ongoing debate, which of these factors and to which extent these factors control the launching of jets. And this is still, again, a very interesting and productive subject of study. The final points I will make on the radio selected active galactic nuclei is that, well, the radio spectrum that we observe from these radio loud AGNs is typically of a power law form. It is thought mostly to be from synchrotron emission, sometimes with synchrotron self-absorption, but unfortunately, usually there is no redshift information provided by the radio data themselves. So one has to then go and get spectra, for example, in the optical band to get redshifts for all these radio sources. Furthermore, the radio emission is often affected by beaming. Again, the classic example of that is the case of blazars, which I referred to earlier on, where you have beamed radiation from a jet that's pointed right toward the Earth. And this beaming effect can be a major complication when trying to do proper surveys of the demographics of active galaxies out there in the universe, because the beaming can make some sources appear much brighter than they actually are, and so on. And one has to untangle all of that before one can even start doing reliable demographic work. Another advantage, just in passing again, is that radio emission is generally not extincted by dust. And so that's, again, a big surveying advantage, because you don't have to worry about dust making it hard to find these radio loud active galactic nuclei in general. And then finally, when one goes and identifies these radio loud active galactic nuclei and investigates them, one finds that most, not all, but most luminous radioactive galactic nuclei lack prominent AGN signatures in the optical. Many of them do not show a strong accretion disk continuum. Many of them do not show strong prominent broad lines. And so these sources, appear to be of a rather different nature than the optically selected ones, which almost, by construction, and at least in most cases, have a strong discontinuum and have strong broad lines, because that's how they're being found. And in fact, this is a key example comparing the radio population to the optically selected AGN population. This is a key example of how different selection methods for active galactic nuclei often find very different AGN populations. And this goes to this classic little cartoon shown down here, where in this case you have a bunch of blind men looking at an elephant, and they each feel a different part of the elephant, and the man holding the trunk says, well, I think an elephant is like a snake because its trunk is shaped like a snake. And then this man holds the elephant's ear and says, well, I think an elephant is like a rug because the ear is big and flat like a rug. And then, this person touches the elephant's tusk and says, well, an elephant is like a spear because the tusk is, strong and pointy like a spear, and so on. You can see here's someone holding the tail, thinking it looks like a rope, and so on. And the point here is that, active galactic nuclei are complex objects, as is an elephant. And if you only study them, at a particular wavelength or something, you may get a rather incomplete picture, just as, this blind man thinks an elephant is like a rug, because this blind man cannot appreciate the full complexity of an elephant. And this point is, highlights how essential multi-wavelength investigations and surveys of active galactic nuclei are for getting a complete understanding of these systems. A single wavelength will not do. You'll get an incomplete selection. And for example, if you only found active galactic nuclei via the radio method, it had never found them with any other methods, well, then you would deduce that most active galactic nuclei don't have very strong continua from accretion disks, generally, or at least often do not have broad lines. But in contrast, you would be, of course, missing the optical population, which has those things. Okay, so this complexity, in fact, this basic point, is a key reason why AGN terminology, which I will talk about in more detail in a little bit, is still quite a bit of a mess. So now that we have talked about the ground-based surveys, I would like to continue and talk about space-based surveys for active galactic nuclei. So we're going to go back to our electromagnetic spectrum here, and space-based surveys are required to study active galactic nuclei in surveys in regions where the atmosphere is opaque, including the high energy band, the X-rays and the gamma rays, including the far and mid-ultraviolet, including the infrared band, and so on. Now, space missions, in contrast to ground missions, are very expensive. It just takes a lot of effort and money to put something in orbit or beyond. And moreover, their technology tends to lag behind ground-based technology, owing, to the rigors of the space environment. Technology has to be radiation hardened and so on. And so those basic facts make space-based surveys for active galactic nuclei very challenging. But nevertheless, space-based surveys offer some truly fantastic advantages. And one can understand that by just considering the Chandra X-ray Observatory, which is one of the leading X-ray observatories right now. It has a rather limited collecting area, ballpark between about 300 and 600 square centimeters. Its collecting area for, a several billion-dollar observatory is only comparable to that of a dinner plate. Okay, so that doesn't seem very impressive, but nevertheless, despite that limitation, the Chandra X-ray Observatory has made fundamental contributions to AGN surveys. Here again is this plot I showed you before of X-ray surveys, and the Chandra X-ray Observatory has conducted many of the most sensitive X-ray surveys that have ever been performed. That's the regime where Chandra, in fact, is dominant right now, at least. And this shows the power of space-based surveys. While they're very challenging and expensive to do, accessing these unique other parts of the electromagnetic spectrum can be incredibly illuminating and can allow major advances to be made in AGN surveys and, of course, more broadly as well. So I'd like to start, in fact, by talking about X-ray surveys, since we're on the topic. And I'd like to highlight that X-ray surveys have some real advantages for studying AGNs. First of all, the X-ray emission that we observe from active galactic nuclei is thought to come from that accretion disk corona that I referred to in the last lecture. And sometimes it may also come from relativistic jets. And we now know empirically that while this accretion disk corona structure is still rather mysterious, it appears to be very robust and is nearly universal among luminous active galactic nuclei. So you can count on the X-ray emission being there. That's this point. Another very important advantage is shown here by this plot. And this plot is highlighting that X-ray emission is highly penetrating and has rather low obscuration bias. What I'm showing here is a typical X-ray spectrum, a broadband X-ray spectrum, spanning 3 orders of magnitude in energy of an active galactic nucleus, and I'm adding absorption to it of different column densities. And these numbers here show the column densities, and to give you a sense, a column density of about 10 to the 23 is comparable to the column density through your hand. About 10 to the 24 is comparable to the column density through your chest. And you can see that these higher energy X-rays are hardly affected, even by very large levels of obscuration that would totally prevent optical light or ultraviolet light from getting through due to the dust. The X-rays can burrow through that obscuring material and allow active galactic nuclei to be found. And that's extremely important because, as I alluded to earlier, we now know that most active galactic nuclei out in the universe are significantly obscured, and one needs a penetrating form of radiation, such as X-rays, to be able to find them. And then, furthermore, we also know that X-rays have low dilution by host galaxy starlight. That is illustrated by this plot here that shows an optical image of an active galactic nucleus, and then the same active galactic nucleus observed in the 2 to 10 keV X-ray band. And you can see that all the starlight drops out, and the black hole related light from the supermassive black hole is the dominant source of radiation, very clearly. And so, again, X-rays maximize the contrast between starlight and black hole related light. Now, there can be X-ray binaries and so on in some galaxies that can compete a little bit with the active galactic nucleus, but unless you go down to very low AGN luminosities, usually the AGN stands out quite clearly and can be straightforwardly found via the large contrast against the starlight. Okay, here are a couple of examples of deep and wide X-ray surveys. Here is the deepest X-ray survey that we've ever done. This is the center of the Chandra Deep Field South. This is a 7 million second exposure with the Chandra X-ray Observatory. You can see all these X-ray sources that were detected here, many of which, about half or so of which, are in fact active galactic nuclei out in the distant universe. Now, I also want to then highlight wide area X-ray surveys. Here is a modern example of a wide area X-ray survey. This is the E Rosita All Sky Survey. They have surveyed the entire sky to quite good sensitivity, in this case in the 0.3 to 2.3 keV X-ray band. And you can see these little specks at high galactic latitudes generally. Many of these are active galactic nuclei. Okay. Down here in the bottom is another wide area survey. This is the Swift BAT All Sky Survey, conducted at higher energy X-rays, in this case in the 14 to 195 keV X-ray band. And again, you detect many active galactic nuclei here. Most of these data points at high galactic latitudes are active galactic nuclei that have been found via their high energy X-ray emission. One point I want to highlight there is that X-rays span a very broad band. Remember that, of course, the optical band is only about a factor of 2 or so in wavelength or in frequency or in energy, whereas the X-ray band is incredibly broad, running from here 0.3 keV at the low end of the E Rosita All Sky Survey up to pushing 200 keV at the very high energy end of the Swift BAT survey. And so E-Rosita and Swift Bat are about as different as mid-infrared and ultraviolet light. So the point I'm trying to highlight here is that the X-ray band gives you a very broad sort of grapple hold on the electromagnetic spectrum. There's an incredibly broad range of energies or frequencies there, and correspondingly incredibly broad range of information. You can also see that back here with this plot, where again, notice this plot spans 1, 2, 3 orders of magnitude of energy in this case, much, much broader than the factor of 2 in energy that corresponding to the entire optical band. Okay, now multi-wavelength comparisons have shown that X-ray surveys, particularly up at higher energies, above about 2 keV, are extremely efficient at selecting active galactic nuclei with high purity. Ultra-deep X-ray surveys, in fact, have provided the highest AGN sky density found at any wavelength. Here is a plot that illustrates that. This is the AGN sky density, the largest AGN surface density found in objects per square degree in the radio band, in the near-infrared band, in the optical band, in the X-ray band, and in the gamma ray band. And you can see that the X-ray band wins, and it wins by a wide margin. Okay? Ultra-deep X-ray surveys provide the highest AGN sky density. In fact, in the center of the Chandra Deep Field South, we get up to more than 20,000 AGNs per square degree. Now, that, in fact, implies that there are an impressive billion AGNs across the sky that we have still not detected, and that we could detect in the future if we conduct very wide area surveys at the sensitivity of the Chandra Deep Fields, for example. Now, as in the radio band, the X-ray data themselves usually do not directly give you a spectroscopic redshift. X-ray spectroscopic redshifts are rare. Sometimes the X-ray spectra, in fact, do give you a redshift via detection of the iron K line in the X-ray band, for example. But usually that's not possible. And so you typically need optical near-infrared spectroscopic follow-up to get redshifts, or you need to utilize broadband optical near-infrared colors to derive photometric redshifts. And getting redshifts is a rate-limiting step for the X-ray surveys, as it is for the radio surveys, and as it is more broadly throughout AGN surveys. And I'll say more about that a little bit later. Now, if you go beyond the X-ray band and you go up to the gamma ray band, well, there are many more orders of magnitude in energy or in frequency. Gamma ray sources, gamma ray blazars in particular, are detected up to about 7 decades in frequency above the X-rays. So here, that's about 150 keV that I'm labeling there. That's the end of the X-ray band. And you can see there are many more orders of magnitude here as you go up through the MEV gamma ray band, through the GeV gamma ray band, and even up to the TeV gamma ray band. Okay? Now, in these very high energies, you mostly detect jet-related emission from active galactic nuclei. And in fact, you generally detect jet emission from the rare subset of active galactic nuclei that first have powerful relativistic jets, and then secondly have those powerful relativistic jets that happen to be pointed at the Earth. That is the blazars. Okay? Mainly at these very high energies, you detect blazars. You also detect some radio galaxies, again, that have jet emission in them. Now, these gamma ray surveys have been conducted very effectively now. Here, for example, this plot at the bottom shows the Fermi-Lat, I believe, 14-year source catalog in the 50 MeV to 1 TeV band, and they detect now about 3,600 or even somewhat more gamma ray emitting blazars with the Fermi satellite. And then at even higher energies, one can use ground-based gamma ray detectors, such as the Hess instrument and others. This one spans 0.1 to 100 TeV, and it detects objects, again, gamma ray blazars up at very impressive TeV energies. Okay. Now, these gamma ray AGN surveys, have advantages that they do point the way to extreme jet physics, They highlight objects that have powerful jets that are pointed right at Earth. They let us identify these systems and study their jets. And that's very interesting. And impressively, some of these gamma ray blazars that have been found, in fact, are detected all the way from the radio up to the very highest energy gamma rays, spanning 18 decades in frequency, which is very impressive to have a source that's detected over 18 decades of frequency. But the gamma ray blazars are indeed detected like that. The downside, perhaps, of gamma ray AGN surveys is they have very severe incompleteness, because generally, up in the high energy gamma rays, you only find the objects with powerful jets, and you only find those, again, at very high energy gamma rays when the jets happen to be pointed right at the Earth. And for that reason, the gamma ray AGN surveys have severe incompleteness. They are rather poor for surveys of the general AGN content of the universe. And that is why, going back to this plot, the X-ray surveys you can see are orders of magnitude more effective than the gamma ray surveys up at very high energies. Because again, there you're only finding a small subset of active galactic nuclei. Now, the ones you find are very interesting, but they're a tiny subset. Okay. So we've now dispensed with the high energy bands. And I also want to say just a few words about mid-infrared and far-infrared AGN surveys. In the mid-infrared and far-infrared, you are often, or in fact usually, looking at dust. And that dust has been heated up by an energy source. The energy source can either be the active galactic nucleus, when it shines up, for example, out upon this toroidal structure, it can heat up this toroidal structure, causing it to produce mid-infrared emission at shorter infrared wavelengths. Or at longer infrared wavelengths, you're generally looking at dust that's been heated up by stars in the host galaxy of the active galactic nucleus. No matter which of these cases applies, whether you're looking at sort of the mid-infrared or the far infrared, you're generally looking at waste heat. You're looking at re-emission of radiation that was originally produced at shorter wavelengths, but has been absorbed by dust and is being re-emitted as, again, what is referred to as waste heat. Now, these mid-infrared and far-infrared surveys also have the basic observational constraints, and they also follow their own wedding cake type diagrams. Here is a wedding cake diagram for 4.5 micron surveys. Here is one for 100 micron surveys. Okay, so again, this basic fact of life applies everywhere across the electromagnetic spectrum. And people have developed, for example, in the mid-infrared, quite effective ways at selecting active galactic nuclei. Generally, what they rely upon is infrared colors, and people have developed little recipes that let them select active galactic nuclei in sensitive mid-infrared data. Often, for active galactic nuclei out in the mid-infrared band, the infrared spectrum is roughly like that of a power law, and so that power law shape makes the colors of active galactic nuclei fairly distinctive compared to other sources in that band. And so you can see here in this plot, in this case it's the 3.4 micron minus 4.6 micron color compared to the 4.6 minus 12 micron color. And here are active galactic nuclei. These are the characteristic colors they have, which are generally distinctive from that of stars and elliptical galaxies. But as you can see, there is some non-negligible overlap with other sources like starburst galaxies and luminous infrared galaxies. And so the challenge, as I allude to down here, is that because you are generally studying waste heat from these systems, mid-infrared selection often suffers from contamination by star-forming galaxies. Especially this is the case at low AGN luminosities, where you also have a significant contribution, or can have one, from the host galaxy. So unlike X-ray based selection of active galaxies, infrared selection is often not very pure. On the other hand, infrared emission does have some real advantages. It is relatively obscuration free. It can, again, penetrate through large amounts of obscuring material. That's especially the case beyond about rest frame 6 microns. And in fact, infrared selection in the mid-infrared has even found highly obscured active galaxies that are missed even in the X-ray surveys. So this is a very powerful complement to the X-ray surveys. It has real advantages, being relatively obscuration-free, but it does have challenges as well. In particular, this confusion with star-forming galaxies. This is particularly problematic, at least at sort of moderate or low AGN luminosities. Okay, just to show you a couple mid-infrared AGN selection results. Here's one that's rather nice. Using data from the WISE survey, this is a wide field infrared satellite. Here they have been able to select about 4.5 million active galactic nuclei, because you have a lot of data covering the entire sky and quite good sensitivity, and they've been able to select those with something like 90% reliability. Okay, and here you can see magnitudes for these sources in different photometric bands. We've also found particularly interesting, luminous, remarkable active galactic nuclei out in the mid-infrared. We've found, for example, what are known as ultraluminous, hot, dust-obscured galaxies, or hot dogs, a rather embarrassing acronym, but there it is. And there are these sources here that they find that have these show very hot dust emission that they think in many cases is being heated up by an active galactic nucleus. And indeed, X-ray observations of some of these ultraluminous hot dogs indeed reveal obscured active galactic nuclei in many of them. So here's a case where the mid-infrared and the X-rays are working productively with each other to identify systems that would be hard to find from either method alone. Okay. And then finally, of course, I feel it important to mention the James Webb Space Telescope, which is now conducting revolutionary mid-infrared surveys over relatively small areas of sky. So here are the various instruments on the James Webb Space Telescope, and it is now conducting, through the mid-infrared, fantastically sensitive surveys, reaching down to like nanojansky flux levels. But these are conducted generally over rather small sky areas. Here, for example, this is the JADES survey, and you can see here that each one of these spans is about 5 arc minutes. So this is a rather small area of sky observed with a lot of James Webb Space Telescope time to fantastic levels of sensitivity. And this is allowing people to identify new interesting active galactic nuclei at high redshift, for example. And again, there's much complementarity between, for example, the ultra deep data from the James Webb Space Telescope and the very deep X-ray surveys, for example. So again, James Webb Space Telescope is now conducting new revolutionary surveys with fantastic sensitivities in the mid-infrared, but over relatively small solid angles. But there surely is a lot of great science coming out from that as well. Okay, so I will end our discussion of multi-wavelength AGN surveys with a few future prospects. First of all, I want to highlight there still are some big questions out there for AGN surveys still to address. We still need a better understanding of the growth and feedback of highly obscured supermassive black holes through the era of galaxy formation, broadly between redshifts of about 1 and 4. We're chipping away at that big problem right now, and as additional AGNs are found and studied from the multi-wavelength surveys, I expect we'll make good progress there. We also want to better understand supermassive black hole growth in the first galaxies at redshifts of like 6 to 10. And we'd also like to understand the even higher redshifts, perhaps redshifts of 10 to 15, seeds of supermassive black holes. This is another big topic of interest. And X-ray surveys have made some contributions there. The James Webb Space Telescope is now making important contributions there. So we're chipping away at that one too right now with AGN surveys. We also would like to develop a deeper understanding of AGN galaxy and AGN large-scale structure connections. We have made real progress there, but there is much more work still to be done. And then finally, we would like to complete our understanding of AGN obscuration. The obscuration of AGN, as I'll talk about in a future lecture, is complex. It's much more complex than just that simple toroidal donut structure. We believe there's obscuration by winds. There can be obscuration by the accretion disk itself, as well as by a variety of other structures. In fact, the interstellar medium of high redshift galaxies may often cause substantial levels of obscuration. So really understanding AGN obscuration well is something that we're chipping away at, but there is surely much more work to be done. Thankfully, we have many powerful surveys coming to address these things. If you consider just wide field AGN surveys, well, you have observatories coming like the Rubin LSST, like Sumeray, and those are in the optical. In the infrared, you have Euclid now going, and you have Roman coming in the future, and you also have Spherex coming. And so those will make big contributions to finding and understanding active galactic nuclei at infrared wavelengths. And then in the radio, well, you have ASCAP and MeerKAT. In the future, people look forward to the square kilometer array. And so there are many great wide field surveys coming, wide field survey facilities coming, that will advance understanding of active galactic nuclei as well as many other cosmic sources. And together, we aim to select something like 50 to 100 million reliable active galactic nuclei from all these facilities working together, reaching out to very high redshifts of perhaps 9 to 10 or beyond. There also are many deep field AGN survey facilities coming. Athena, which is a very powerful X-ray observatory, will be coming perhaps in the mid-2030s. Another mission called Lynx would be much more sensitive to the Chandra X-ray Observatory. There are a variety of spectroscopic facilities coming online that will be very powerful for advancing our understanding of AGNs. There are great sub-millimeter surveys coming online. There are radio surveys advancing rapidly. And of course, these deep field survey facilities are essential for faint source science, for example, often at the highest redshifts. And they are also essential follow-up facilities for AGN subsets from these wide field surveys. You can identify objects for interesting AGNs from these wide field surveys and then target them intensively with these narrower field instruments to get much higher quality data to understand them better. One general point, which I alluded to in passing earlier, and I want to say a few more words about, is that there remains an enormous need for more and always better AGN spectra. There are many spectroscopic AGN surveys that are planned or ongoing. Here are a few of them shown here with these various sort of logos or brands. And unfortunately, spectroscopic follow-up remains a major rate-limiting step for much AGN science, despite their relative affordability. What I mean by that is that, again, we have many costly space missions, the Chandra X-ray Observatory, XMM Newton, now Euclid, for example, that are going to generate enormous samples of fascinating active galactic nuclei. But the challenge is getting just spectroscopic redshifts as well as valuable spectroscopic diagnostic information for these sources. And this has remained the case for the 25 years I've been playing the game. And it's sort of unfortunate because, again, these ground-based spectroscopic surveys are relatively affordable compared to these billion-dollar class space missions. And they often are a rate-limiting step for extracting the best possible science from the billion-dollar space missions. So, one almost could suggest that if you're going to bother to build a several billion-dollar space mission, you might as well spend an additional 10% to build a dedicated ground-based spectroscopic facility that is appropriately tuned to do follow-up of all the sources that your space mission generates. Unfortunately, that approach has generally not been taken, but it would, it arguably could make a lot of sense. Thankfully, photometric redshifts and narrowband photometric surveys do help in generating large numbers of usually pretty reliable redshifts, but nothing, of course, is as good as a good solid spectroscopic redshift. And so one hopes that many of these additional spectroscopic facilities will be produced and will be used to turn a lot of the wonderful data that we have, often sitting in archives, not properly utilized, into great science. I also want to make another point, and that is the issue of wanting to fill the available discovery space of AGN surveys. So we of course want surveys that discover new unexpected AGN phenomena. We don't want surveys that only answer predefined questions. Clearly answering predefined questions like the ones I laid out here is a very good thing. But you also want facilities that just explore discovery space and generate new unexpected discoveries. That has been the historical way that many discoveries, or many of the best discoveries across all of astronomy, have happened. Now, I would say that we are doing a solid job right now, overall, of filling the broad discovery space, which has axes including wavelength coverage and flux and time domain coverage and good spectral resolution and polarization. Although, as I've mentioned, one wants more spectroscopic surveys. One could do with better, perhaps, polarization surveys. But overall, especially considering the growing financial challenges that many nations have with their budgets, we are doing a pretty good job of filling the discovery space. There are some obvious issues, however. One of them comes from just considering the relative flux limits coming from space missions versus ground-based missions in wide field surveys. So what do I mean by that? Well, here I show the relative flux limit in the ground-based optical for a current generation wide field optical survey, the dark energy survey. And I compare that to the flux limit coming applicable for the Hubble Space Telescope Ultra Deep Field. And the point here is right now that ratio, the ratio of the very deepest optical imaging that we have compared to the very wide field best imaging we have, that ratio is about a factor of 100. The UDF is 100 times more sensitive typically than the dark energy survey. And when Rubin LSST comes online, that will generate a better wide field survey, reducing this ratio to about a factor of 10. So the deepest optical imaging will only be about 10 times deeper than what we have from Rubin LSST. Now, one can compare that ratio with the similar ratio in the X-ray band. For example, the eRosita All-Sky X-ray survey that we have, which is the best all-sky X-ray survey that we have, is about 2,000 times less sensitive than the flux limit that we have in the very deepest parts of the Chandra Deep Field South. And the point I'm trying to make here is that this ratio is much larger than this ratio, and will be even larger than this ratio once this ratio is reduced to about 10 once Rubin LSST operates for a while. And so what I'm trying to drive at here is that space missions still need progress in wide field surveys, and any attempts possible that could reduce this dramatic ratio difference between space-based surveys, here I use X-rays as an example, and ground-based surveys, here I use optical as an example, would be very beneficial to allowing proper balance between ground-based surveys and space-based surveys, and allowing very wide-field space-based surveys to properly complement the corresponding very wide-field ground-based surveys. Okay, and I will end this section just by quoting a few recent reviews that I think may be useful to you. So here are a selection of reviews. I'm not going to read each one out, but if you want to learn more about these topics, here are a set of reviews that might be of value to you. I now want to move on and finish this lecture talking about terminology. Now, AGN names I have been made a big impact, perhaps, in popular culture. Here we have a comic book, Quasar, the Cosmic Avenger. Here, somebody is trying to sell a car by calling it the Quasar, I believe. And so these AGN names are widely used across popular culture. But unfortunately, from a scientific perspective, these AGN names, while they've been very successful in reaching the broad population, they are a bit of a mess. So what I've done in this particular slide is I have written down many of the names that we use when we talk about active galactic nuclei. We talk about Seyfert galaxies, as I've mentioned earlier. We talk about blazars. We talk about low luminosity AGNs and Seyfert 2 galaxies and Seyfert 1 galaxies and broadline radio galaxies and narrowline radio galaxies and BL-LAC objects and radio loud quasars and radio quiet quasars and weak line quasars and OVVs. There's all these names. And I've deliberately here put these names in a kind of a jumble alphabet soup pattern because I'm deliberately not trying to imply any ordering or structure to the names that I'm showing on this slide. Now, these names were developed in general as people were coming to understand active galactic nuclei for the first time. At the time many of these names were produced, people did not have a complete understanding of active galactic nuclei from a multi-wavelength perspective. Kind of like the little cartoon I showed you with the many blind men feeling the elephant, and each one says an elephant is like this and an elephant is like that, and each one of them is very incomplete. Well, it was the same thing with people as they were coming to first discover active galactic nuclei and attach terms to try to describe what they were finding. Now, via subsequent unifications of ideas, many of which I will talk about in future lectures, some of this terminology has been shown not to reflect real, internal, physical, interesting differences. Rather, much of this terminology reflects either confusion coming from when people didn't have a complete understanding, or reflects orientation effects, which aren't all that interesting, and so on. As a result of some of that confusion, the overall terminology of active galactic nuclei can be confusing, and there still is a lot of historical baggage that doesn't have much physical importance to it. So you need to keep that in mind. Furthermore, there is also, even today, now that we do have a much more complete understanding, but even with that much more complete understanding, there is also, even today, fairly sloppy use of AGN terminology, AGN type names, for example, in some of the literature. Sometimes people throw around terms like a type 2 quasar or a blazar in a rather loose way without properly establishing that the object that they're studying indeed satisfies the criteria needed to be properly called a type 2 object or a blazar or whatever else term they're using, according to the actual definitions of these terms as they were originally written down. So what I'm trying to say here broadly is that AGN terminology is somewhat of a mess due to these reasons, but unfortunately it is too late to redo all the terminology more logically. And so to be able to do the work on AGNs, you just have to learn this terminology. And so I will, in a minute, give you a couple of slides that help you, link observed properties to names for active galactic nuclei. Now, all of that being said, despite the fact that much of this terminology is a bit of a mess, I do think that there are some key classification variables that do lead to fundamental insights. One of them, for example, is the strength of radio emission. As I've mentioned, about 10% of active galactic nuclei, the radio loud objects, a classic example are the radio loud quasars, but there are others, learn a trick and are able to produce powerful relativistic jets. while the remaining 90% of active galactic nuclei don't learn the trick of being able to produce powerful relativistic jets for whatever reason, and they are radio quiet. So that is a fundamental difference. Some AGNs learn to produce powerful jets, other ones do not. Why is that? Well, that's an interesting, fundamental, physically interesting question. That's not a boring historical artifact or some sort of sloppy usage of terms. That's actually something really physically interesting that's worth trying to understand. Another one goes to this issue of optical ultraviolet emission line properties. As I've alluded to already, we have two types of many active galaxies. We have the type 1 objects, like the Seyfert 1 galaxies, and we have the type 2 objects, like the Seyfert 2 galaxies. Another example is the type 1 quasars versus the type 2 quasars. The idea here, roughly speaking, goes back to that issue of orientation, anisotropic orientation. And if you have anisotropic obscuration. And if you have obscuring material and you tip it in different directions, you can get very different observed phenomena. In general, the type 1 objects are thought to be objects where the obscuring material is not along the line of sight very much, so perhaps viewed pole-on for obscuring material that is in the equatorial plane, whereas the Seyfert 2 or the type 2 objects in general, objects where the obscuring material is in the line of sight, so viewed in an equatorial manner rather than a pole-on manner. So that is a interesting physical distinction that has arisen, much of which has arisen due to studies of optical ultraviolet emission line properties. And there are other names there too. There are broad line versus narrow line radio galaxies, where again, these are the ones that are generally thought to be viewed roughly pole-on. These are the ones that are thought to be viewed more in an equatorial direction. And then there are also other complications. There are intermediate Seyfert types where some of the lines are narrow, other lines are broad, so they kind of appear to be a bit of a mixture of type 1s and type 2s. I'll say more about them later. And then there are other remarkable objects. There are narrow line Seyfert 1s, there are BLACs and weak line quasars. These are other remarkable objects that are identified by their optical ultraviolet emission line properties. Another important classification variable is variability. Some AGNs are much more variable than others, and there are physically interesting reasons for that that we want to understand. Another example are ultraviolet absorption line properties. Some objects show strong ultraviolet absorption lines from powerful winds lying along the line of sight. Other ones do not, and we want to understand that. Those are examples of interesting classification variables. I will say that luminosity is often also used in classifications, although that is, I believe, largely for historical reasons. Usually we think luminosity is not so fundamental. For example, the Seyfert galaxies are just low luminosity versions of the quasars. We don't think the quasars are fundamentally different from the Seyfert galaxies. We just think that the Seyfert galaxies have the volume control of the active nucleus dialed down a little bit, whereas the quasars have it dialed up. These are connected by a continuum of luminosities rather than being physically distinct groups. So luminosity is probably not a really fundamentally that interesting classification variable, although of course it is interesting to ask, why are some systems more luminous than others? Why are they accreting more strongly than others? And we'll talk about those issues later on as well. Okay, so here, as promised, is a so-called AGN bestiary. This is from Julian Krolik's textbook, and it basically gives you a set of observed properties. Is an object point-like? Does it have broad lines? Does it have narrow lines? Is it a strong radio source or not? Is it variable? Is it polarized? And then based upon the observed properties that these sources have, it links you to the type of object that it is, whether it's a radio loud quasar, a radio quiet quasar, an OVV, a BLAC, a Seyfert type 1, a Seyfert type 2, and so on. Okay, so basically here you have a little truth table that lets you link observed properties back to what you should call the thing following its name. Krolik also gives this nice diagram which shows a schematic of the principal subvarieties of AGNs arranged according to their emission line widths, their radio power, and their degree of variability. And these three variables serve pretty well as a way of separating out AGN properties. And notice these three axes correspond to the key class, at least many of these key classification variables: strength of radio emission, emission line properties, variability, that I talked about here. So here it is shown graphically. Okay. And then finally, here is another schematic, one that I will talk about in more detail later, that highlights that orientation-based unification model. This is from the book by Beckman and Schrader. And here, they separate this out into objects that are radio quiet down here and objects that are radio loud up here. And notice that for the radio loud objects, they show a powerful jet being generated, while that jet is not present down here in the bottom part of this diagram for the radio quiet objects. And then they label quite conveniently that, for example, just among the radio quiet objects that are observed in a relatively pull-on manner, the Seyfert 1 objects, or the type 1 objects more generally, are objects where you can observe down and see the central regions directly, whereas the type 2 objects, or the Seyfert 2s, have obscuring material blocking our line of sight down into those central regions. And that obscuring material, either being out of the line of sight or in the line of sight, can make very strong observational differences among an object that is fundamentally the same. Similarly, the radio loud AGNs have their own classifications. It gets even more complicated because you have to consider whether this jet is really powerful over here or lower power over here. And sometimes a jet could be pointed right along the line of sight, in which case you get the blazars, and they have their own subtypes, and so on. And the whole thing can get to be very complicated. I'm not going to belabor this for now. We'll talk about it more later on. And that is the end of this quick review of terminology, as well as the end of this lecture. Thank you.